Another session on mobile communication and networks. A very good afternoon to all. Good afternoon, Harshita. Thank you for your feedback. I hope you all are able to hear my voice.
Yes, sir.
We'll start today's presentation. Yeah, thank you, Jashwant. So we shall start unit number 2. I hope you would have received the materials for unit 1, the assignment for unit 1 also, most in Google Classroom. Most of you would have joined the Google Classroom, but only 3 members are still pending. So I'll identify those 3 members, and through your class in charge, I'll intimate to them such that they join the Google Classroom at the earliest. Okay.
Sir, those are 2 marks questions or long answers, sir.
They're not specified as 2 mark or 4 mark or 6 mark or 10 marks or 16 marks. Those are not specified marking types. It is to make you understand what the topic is. How much you had understood, that much you can find it.
Okay, sir. Thank you, sir.
Okay, the main purpose of assignment is to evaluate yourself such that how much depth of knowledge you are having in that particular topic or in that particular question or in that particular problem. Okay, it doesn't matter you script it for half a page or you script it for 16 to 20 pages for a single question. It is to learn in-depth knowledge about that particular topic. Hope you understood this point, Yashwant.
Yes, sir.
Yeah, thank you. And I require a CR or your representative to contact me personally after the classes, such that if anybody is having a doubt in mobile communication, they can contact me directly. Request CR, if there is any WhatsApp group available for your class, you can add me. I'll give my number to CR, or you can create an new WhatsApp group for mobile communication and networks class for all of your classmates, 60 members. If it is existing, you can add me, or else if you feel that not to add, you can create a new group and everyone can add in that. So I hope I don't know who is the CR, so I don't. They can contact me personally. I'll request your class in charge to give my mobile number to you. So mobile communication and networks, unit 2. So this unit 2 is divided into two parts. For presentation, I divided into two. One is the part 1. Okay. So unit 2 is the wireless channels. This is the title of the unit. So let us see what we are going to say in this uh, part 1. So part 1 we are going to see about signal propagation. So what is a signal? It propagates in wireless. Everything is in wireless. Since we are doing the unit in wireless channel, everything is in wireless. Okay, so the communication medium that we are discussing here is wireless. So the signal propagation mechanism, so where there are three different, there are four different mechanisms. One is the reflection of a signal, refraction of a signal, diffraction of a signal, and scattering of a signal. Okay, so we'll be seeing these four different concepts or four different characteristics of a signal propagation. So then we'll be moving on to the large scale signal propagation. Large scale signal propagation and its associated mechanisms and characteristics. Then we are going to see the uh, small scale fading with respect to the multipath characteristics. The large scale fading and small scale fading in mobile radio propagation, especially the multipath fading. Okay, so this we are going to see. Then followed by an important concept in small scale fading is a Doppler shift. So this is what is present in this part 1 presentation. So let us see what is this signal propagation is. Okay. So before starting the signal propagation, first we need to know, we need to answer these questions. So the questions are, the first question we should ask ourselves. Okay, then we will be able to understand what this signal propagation in wireless channel is. Okay. The first question is that what are reasons that wireless signals are hard to send and receive? Okay. So what are the reasons that the wireless signals are hard to send and receive? If you send it on a wired medium, they are very much easier. You can easily send it to the cable. Till the cable is present, you can easily transmit our signals in electromagnetic wave. Okay. So now the question is, why it is very difficult in wireless signals? Why it is difficult in wireless medium or wireless communication channels? The reasons are, the mobile radio channel places fundamental limitations on the performance of wireless communication systems. So whatever communication we are doing now in mobile communication network is wireless. We are having devices, either laptops, tablets, mobiles, are all propagating through wireless medium. In the sense, air is the medium, channel is air, and the signals are transmitted from one place to another place in space. So there are some limitations for the performance of this wireless communication systems. So there are paths that can vary from simple line of sight to the one that are severely obstructed by buildings, mountains, and foliage. Okay, I'll show you this pathway of line of sight in a simple example or in a diagram, such that you will understand this line of sight in a better way. Okay, so when there is a transmitter and a receiver communicating with each other, the transmitter will send a signal, the receiver will receive it, and especially in wireless communications, when you send the signals from one point to another point, in between the receiver and transmitter, there could be a presence of buildings, large buildings, towers, or all will be present. Mountains will be present, hilly areas or hills, mountain at with the different heights will be present, which obstruct the path of line of sight. So, which will obstruct the transmitted signal such that it doesn't receive at the received signal. So, foliage is that dense trees, denser trees. The denser trees will have more leaves. So these leaves will obstruct, or they will act as a barrier in between the transmitter and receive signals. So now to achieve the simple line of sight, these are some of the obstacles that are being observed in wireless communication. So this is a reason why wireless signals are hard to send and receive. One of the reasons. So third reason is that radio channels are extremely random and difficult to analyze. So the radio channels are randomic in nature and are very difficult to analyze. So that is another reason why wireless propagation are really hard to transmit and receive it back. So next is the speed of motion of the receiver plays a major role in determining the signal level. When the transmitter is at a fixed point and the mobile or the user is in motion, and if he is moving at a faster speed, so the signal level will vary. An appropriate threshold level will not be obtained. So this is also a main reason why wireless communications are really hard to send and receive. Okay. So all these 4 points that we are discussed now, or we are answered for this question, is what we are going to see in this unit number 2. Okay. Relevant characteristics, relevant mechanism, the relevant procedure to overcome all these limitations, and effective utilization of the bandwidth and channel, and increasing the spectrum utilization and increasing the data rate also is possible. It is possible only when you all are familiar with this wireless channels. Okay. So let us see some of the unique problems to the wireless communication system. The first problem is that interference. So as we had seen in unit 1, the term called co-channel interference and adjacent channel interference. So these two interferences are a major problem towards the design of the efficient wireless communication system. So the interference may be due to the other service providers, like we have what we call Airtel, Idea, Geo. Interference may occur due to these other service providers in mobile. In India, I'm talking about. I'm talking about India. They may interfere with each other since they use common towers nowadays. interference may come. Then interference from other users in the same network. If Airtel or BSNL, if the users are there, for example, you take BSNL, if users are using the same network, they may get adjacent channel interference. So this interference is a major problem or a major barrier for designing an efficient wireless communication system. So CCI is your channel co-channel interference, which is due to frequency reuse factor. ACI is adjacent channel interference due to transmitter and receiver. TX I had written it as in TX represents your transmitter, RX represents your receiver. Now to make the presentation a bit interesting, I had wrote it in like this. So keep in remembrance TX wherever it is present is transmitter, RX is receiver. So the adjacent channel interference due to transmitter and receiver design limitations and large number of users using the same bandwidth. BW is a bandwidth. Using the same bandwidth also is a problem. The next problem is your shadowing. Then obstructions of line of sight paths causes areas of weak signal strength. So that we had seen now the previous uh, slide. Obstacles by tall buildings, foliage, and mountains or hills will cause the signals being received at your receiver to be weaker. Okay. So, now let us see the what is this solutions or how this problems arises for the wireless communication system. Okay. So the mobile radio channel which we are using places fundamental limitations on the performance of wireless communication systems. So the transmission path between the transmitter and receiver can vary from simple line of sight as we had seen here, simple line of sight to the one which are obstructed by buildings, mountains, and foliage. So unlike the wired channels that are stationary, the wired channels are stationary, they are predictable. So radio channels are extremely random. So, in wired channels, the radio channels are extremely non-random, whereas the wireless radio channels are extremely random, and the analysis is very much difficult. So modeling the radio channel has historically been one of the most difficult parts of the mobile radio system design and is typically done in a statistical fashion based on the measurements made specifically for some type of good communication system, or it was used for a better spectrum allocation system. So the mechanisms behind the ultramatic wave to propagate, why we are using ultramatic wave is that all the wireless communication channel or the wireless communication uses your radio frequency RF. So RF radio frequency will have only ultramatic waves with the same principles. So each and every ultramatic wave should satisfy the Maxwell's equation. You will be having 4 Maxwell's equation. If all the 4 Maxwell's equations are satisfied, then only that wave is called as an ultramatic wave. So the mechanisms behind this ultramatic wave propagation are diverse, but they can be generally given in terms of the 4 different mechanisms which we had seen. as reflection, diffraction, and scattering. So most of the cellular radio systems, when you see, most of them operate only in urban areas. In rural areas, the presence of these mobile cellular radio networks are very much lesser, since the users are very much lesser there. The mobile radio users at rural places like villages or hilly areas are all very much less. So there is no direct line of sight between the transmitter and receiver in the urban areas. You may have good line of sight. So in these places where no clear line of sight is present, the signals received at the receiver will have some reflections, obstructions, diffractions around the obstructions. So which we call it as a single term called as fading. That is what is being given in bold. FADING. Due to the multiple reflections from various objects, the electromagnetic waves will travel along the different paths of varying length. Then the interaction between these waves will cause multipath fading at specific locations. And the strengths of these electromagnetic waves will decrease as the distance between the transmitter and receiver increases. As the distance between the transmitter and receiver increases, the signals will undergo multipath, multiple reflections, will undergo multiple reflections. So that multiple reflections are due to the various objects being present in between the transmitter and receiver. So as the electromagnetic wave travels through these different paths of varying length, they cause multipath fading at specific locations. So that location will experience a signal called multipath signals. So the multipath signals can be received that interfere with each other. So this is due to a main reason called as increase in distance between the transmitter and receiver. So if the distance between transmitter and receiver increases, the electromagnetic wave signal strength will decrease due to multipath signals. So in fixed wireless channels, the characteristics is that it is random and unpredictable, and it must be characterized in a statistical fashion. So fading must be characterized in a statistical fashion, and the field measurements need to characterize the radio channel performance, which is a main problem of your wireless systems. So these are the mechanisms that affect the radio propagation in a wireless communication system. First one is the reflection, diffraction, scattering, then multipath fading. So as I said earlier, in urban areas, there is no direct line of sight between the transmitter and receiver, where the presence of high-rise buildings can cause diffraction loss. So multiple reflections will cause multipath fading. So let us see what are these reflection, what is diffraction, what is scattering. First, let us see reflection. The propagation models are focused on predicting the average received signal strength at a given distance from the transmitter, as well as the variability of the signal strength in close to the received signal at a particular location. So the average received signal strength at this point can predict the mean signal strength for an transmitter receiver distance, or the transmitter receiver separation distance. So these propagation models are useful in estimating the radio coverage area of the transmitter, and they are called as large scale propagation models, as they characterize the uh, signal strength over a larger transmitter receiver distances. Meaning is that if the distance between transmitter and receiver are from several hundreds to thousands of meters, from the transmitter to the receiver, the propagation model that can be used for analyzing the characteristics of the average received signal strength is large scale fading. Large scale propagation model. Large scale propagation model. And if the distance is very much shorter, or if the time duration of the communication is very much shorter in time, in the order of seconds, so the average received signal strength has to be calculated. So for that, the small scale propagation model is being used. You can see that here two models, the large scale propagation model and the small scale propagation model. Large scale for larger distances, small scale for smaller duration of time or smaller travel of signals, or at a smaller travel distance. Large scale and small scale. So as a mobile moves over a very small distance, the instantaneous received signal strength may fluctuate rapidly, giving rise to a small scale fading. The reason for this is that the received signal is sum of many contributions coming from different directions. In small scale fading. Why do we do the sum of this contributions coming from different directions is that The phases are random in nature. The sum of contributions vary widely. That obeys Rayleigh fading distribution. So this is the reason. So in small scale fading, the received signal power may vary. The received signal power may vary as much as 3 to 4 times. 3 to 4 times it may vary. If you measure in decibels, it is around 30 to 40 decibels. 30 decibels or 40 decibels. So as the mobile moves away from the transmitter over a much larger distance, the local average received signal will gradually decrease. And it is decreasing due to the randomic nature, and this can be predicted only by large scale propagation models. So now let us see what is this reflection, diffraction, and scattering. So I had explained you about large scale propagation and small scale propagation. Large scale fading, small scale fading. So next is the reflection. So reflection arises when the plane waves are incident upon a surface with the dimensions that are very large compared to the wavelength. If this is the case, reflection will occur. Diffraction occurs with respect to Huygens principle. I think you all are familiar with Huygens principle, right? So when there is an obstruction between the transmitter and receiver antennas, secondary waves are generated behind the obstructing body. So that will create press centers, and in turn it may cause diffraction also, which may lead to loss of the information or loss of signals. Third one is the scattering. Scattering occurs when the plane waves are incident upon an object Scattering occurs when a plane wave are incident upon an object whose dimensions are of the order of wavelength or less than that cause the energy to be directed in many directions. The thing is that easily you can understand scattering. Take a drop of water at a distance height, drop it on a surface which is a plane surface. You can able to see that the water get splits up in many directions. So this is an easier phenomenon to understand scattering. So based upon these three propagation mechanisms, the cellular radio propagation is characterized into large scale, small scale, and a medium scale. So large scale is that path loss variation with the distance. Small scale is that fast multipath fading. Medium scale is that slow, log, normal shadowing. So all these things we'll discuss in detail in the forthcoming slides. So each of this propagation is caused by a different underlying physical principle, and each must be accounted for when designing. Each and everything should be considered when you design an efficient cellular system, or each propagation model is to be evaluated for a better cellular systems which you are going to design or deploy. Here is an example of your path loss or large scale effects. Okay, here green color is being drawn: 1, green, 2, 3, 4, 5. 1, 2, 3, 4, 5, everything is in motion. You can see there is a transmitting antenna which is present here. This is a transmitting antenna. So from this transmitting antenna transmit signals to different places. So you can see this first location 1 is the location of a mobile device or a moving device. So at location 1, pre-space loss, that is line of sight, is present, is likely to give an accurate estimate of path loss. So there is no path loss at all. In location 2, at point 2, a strong line of sight is present. So line of sight is this straight line, so from transmitter to receiver. So from transmitter to receiver, straight line, without any obstacles in between. So at point 2, a strong line of sight is present, but this receiver will receive signals from the multiple deflections. Okay, there is another signal which is getting reflected by the earth surface, and it is being focused towards the 2, to the location 2. Okay, ground reflections can significantly influence the path loss. So this uh, planar loss or two-ray model appears here. Location 2 is can be easily determined by two-ray model. So next is location 3. You can see that this device has passed through some of the trees. At location 3, the plane earth losses needs to be corrected for significant diffraction, which is caused by trees cutting the direct line of sight. You can see that there are trees being present. If these trees are not present, the transmitting antenna will transmit directly. Okay. So since trees are present, this device has moved from this location to this location. You need to analyze this losses due to this foliage, and we need to correct it. Okay. At location number 4, you can see that location number 4, the vehicle has moved to location number 4. A simple diffraction model is likely to give an accurate estimate of the path loss. You can use a diffraction model and you can estimate the amount of signal which is being lost. Now you can see this location 3 is at a distance of 20 km. Location 4 beyond that. Location 5 is beyond that, and there in between there are hills and mountains. So at location 5, loss prediction very difficult and unreliable since multiple diffraction is involved. You will be getting diffractions due to this trees, this mountain, and after that it has to receive the signals. So it's a very difficult process. Next is radio propagation mechanism. See the diagram, you have a tower or an antenna which is being placed. Here are two users. User 1, user 2 having a mobile device. Okay. So this mobile device is under line of sight. Why? Because the signal whichever is being transmitted is directly received, which is one circle one. Okay. This mobile user also receives signals, but he receives due to two things. One is by direct line of sight. Second one due to reflections. Next due to diffractions. So 2, 3, and 4. So this we call as non-line of sight. So this user is not directly receiving signals from the transmitting antenna. Instead, reflections from buildings, refraction from a building, refraction from a building, or multiple reflections. So 2, 3, 4. Like this, only this user is getting. So this user comes under line of sight. This user comes under non-line of sight. So I'll give you the line of sight. The line of sight is the direct propagation of radio waves between antennas that are visible to each other. Here the received signal is directly received by the receiver. The effects such as reflection, diffraction, scattering does not affect the signal propagation that much. The radio signals can travel through many non-metallic objects, and the radio can pick up through walls. This is called as LOS, line of sight propagation mechanism. So examples are propagation between a satellite and a ground antenna, or a satellite and a DTH TV receiver at your home, or reception of TV signals from a local television transmitter. This is your line of sight. The non-line of sight is that other than this. Other than that. So any questions till now? You can type in chat box. I'll give you 4 or 5 minutes time. Any queries you can type in chat box. Till this, till the line of sight and non-line of sight. Since I couldn't find any queries in the chat box, I proceed on the next topic. Free space propagation model. This is used to predict the received signal strength when the transmitter and receiver are clear. That is, they are never unobstructed between them, as in this diagram, as one. They are never obstructed by anything. The free space propagation model assumes a transmitting antenna and a receiving antenna to be located in an empty environment. There is no absorbing of obstacles. There are no reflecting surfaces being considered. So in particular, the influence of the Earth's surface is assumed to be entirely absent. So example is your satellite communication system and microwave line of sight radio links typically undergo this free space propagation. Next is path loss. Path loss, signal attenuation is present, which is a positive quantity. It's a positive quantity measured in decibels and is defined as the difference in between the effective transmitted power and received power. The amount of power which is received, the difference with respect to the effective transmitted power at transmitter. So that difference is called as signal attenuation. So FRIS is an application of the standard free space propagation model, where the medium path loss is measured in decibels. So the FRIS free space equation is given as PR of D is equal to PT GT GR lambda square divided by 4 pi whole square D square L. So what is this PR of D? So PR is the received power at a particular distance. PT is the transmitted power, GT is the transmitter antenna gain, GR is the receiver antenna gain, lambda is the wavelength, D is the transmitter and receiver separation distance. The distance between the transmitter and receiver is D. So L is the system loss factor, which is not related to propagation system loss. Okay. For a zero loss path model, always L is equal to 1. Always the signal will fade in proportion of D square. As the distance increases, fading also increases or attenuation increases. The ideal conditions assumed for this free space propagation model can never be achieved in an ordinary terrestrial communications, because in an ordinary terrestrial communication, obstructions will be there, reflections will be there due to tall buildings, obstruction will be there due to foliage, presence of mountains, which leads to multiple reflections from the ground surface. So the free space Model is only valid predictor. It's only a valid predictor. That's all. It cannot give the exact value. So thus in practice, power can be measured at D naught and predicted at D using the relation D greater than or equal to D naught greater than or equal to DF. So where DF is 2D squared by lambda. DF is the Fraunhofer distance, which Fraunhofer distance. So consider and 2 points. So this is a transmitting point, this is a receiving point. Receiver I mark it as P. So this is your reference point. This could be considered for an indoor communication up to 1 meter, outdoor communication valid up to 100 meters to 1 kilometer. So where D is the largest physical linear dimension of the antenna. So we can calculate the received power as PR of D is equal to PR of D naught. So this is D naught into D naught divided by D the whole square. So typically the path loss components will comprise of this. So in free space, the path loss component propagation constant will be 2. In urban area, it will be 2.7 to 3.5. In suburban area, it will be 3 to 5. And in indoor, which is good line of sight, will be around 1.6 to 1.8. So the relation between the average received power and the distance is determined by the expression gamma. So this gamma is the path loss exponent. Which is inversely proportional to the distance. So now let us see an example. Okay. A question is given. Find the far field distance for an antenna with maximum dimension of 1 meter and operating at 900 megahertz. Okay. So the given parameters are operating frequency f. So write it. F is equal to 900 megahertz. The largest dimension, which is the maximum dimension D, capital D, is 1 meter. So then the far field distance can be calculated by this formula. That is question 1. Let me change this. Two D square divided by lambda. So this is the formula for finding this. df is equal to 2d squared divided by lambda. Okay. I require lambda, I require d. So d is known, which is 1 meter. So 1 square I can write. So lambda, I don't know lambda. What is, how to find? I don't know lambda from the question. The question is given only that find the far field distance for an antenna with maximum dimension of 1 meter and operating frequency 900 megahertz. So frequency is given, but lambda is not given. So I can find it by using the formula. Lambda is equal to c by f. So c is velocity of light, 3 into 10 power 8 meter per second. divided by frequency 900 megahertz. So you will get lambda is equal to 0.33. So substitute, you'll get this. So try this example 1, and check whether you're getting these values. I want answers in chat box, those who are getting it correctly. Or I'll give you assessment. Wait. For this you will get this value. But I'll assessment 1 is that 10 meter. Let me see how many of you are getting right answers. The distance is 10 meter. Solve and tell me what is the far field distance. Type in chat box. I'll show the slide again. Then you type the answers in chat box. Anybody who has tried the solution can give me the answer in chat box. 100 kilometer. Let us all. I'll show you. So the lambda will not change. Thank you, Manikanda, for your valuable answer. The lambda value will not change with respect to that problem and this problem because frequency is not changed. It will be as it is 0.33. Only the distance is changing. The distance is the distance d is 10. So formula will become 2 into 10 square 2d squared by lambda. So 2 into 10 square. So 10 into 10, 10 square is
100.
yeah, so okay. 2 into 100 divided by 0.33. Check now what you get.
606.06.
Okay, thank you, Manasa. So Manikanta, I'm not sure how you got 10 kilometer. That's what I'm wondering. Which is 200 divided by 0.33. 606.06 meter is the answer. So how many of you tried and got this answer? If you had got it, type the value that you had got in chat box. This is an important understanding in how to calculate the far field distance. So try and type your what value you got in chat box soon. Such that I can proceed for the next topic. I'm waiting for your answers. After you give your answers only, I'll start the next topic or the next present next slide. I'll move on. I'll move on to the next slide, or else it will be the same. I think you all are still working on that problem. So I'll give you time, no issues. You can do it also. If you're unable to know the formula, you can view the slide. You can view the slide and you can work it out. So I'll put the slide. If you had completed assessment 1, you can type the values in chat box. Those who give the values or those who tried can give their answers in chat box. If you had completed assessment 1, you can do the assessment 2, okay, which I'm showing it here. Assessment 2 question is, find the far field distance for an antenna with maximum dimension of 1 meter and operating at 50 hertz. Compare the previous problem and this problem and you can work it out and give me the answer in chat box. Those who find the answer, those who got the answer, type in chat box. The persons, those who are giving the answers in chat box, only will be given attendance for this session. So work out and give me the answers. It's nice to see that some of you have given answers. Sai Teja Chama has given 0.333, Chandil Kumar 0.34, Atlandeshwari 33.33, okay. Yuvraj 0.3, Trivatsan 3.33, 10 power minus 7, 3.3, 10 power minus 7, Navya, Kirti 0.33, Harshita 33.33, Ravitesh 0.33, Unika 0.33. Okay, no issues. There are so many variations. Let us see. Okay. First, we'll find lambda. Lambda is C by F. Which we know C is 3 to 10 power 8 divided by frequency of 50. We need to calculate this first. How much do you get? 3 divided by 50. You can do it using your normal calculator also. You can do it. Lambda will be 0.06 into 10 power. I think, right? It's a normal calculator. You can do that. Okay. Then we take this value to the physical lambda. So from this 0.06 power. So is 1 1 into 1 will be 2 divided by 2. So lambda. Okay. 2 divided by 0.06. So we get 3.80. So then it goes on and write it as 3.50. Can we rewrite it? Just a minute. Three point three three and 10 power minus 9 or 3.33 nanometer. 3.3 nanometer. So this would be your simplified answer. So using just a basic calculator, you can do it. Not from there. So answer is 0.3 nanometer. So now with this assessment 2, I would like to teach you a thing that is we want to find the far field distance of an antenna with a maximum dimension of 1 meter. and operating at a frequency of 50 hertz. So keep in mind what is this operating frequency of 50 hertz. If you operate a frequency of 50 hertz, it is equivalent to the electrical frequency in India. In India, we use the frequency of operation of an electrical signal is 50 hertz. If you use that, my far field distance is around 3.3 for one dimension. Okay, so for one dimension. So if I use a frequency of 900 megahertz, the far field distance is around, the example is around 6 meter, around 6 meter, considering the dimension as a factor. So this indicates that we cannot use lower frequencies for transmission of your wireless communication. So this is the point which I wanted you to learn. So that's what I had given you an example and assessment 1 and assessment 2. The purpose of this assessment 1 and 2 is to make you learn why we use higher frequencies rather than lower frequency. If you use a lower frequency, it is 50 hertz is a lower frequency as compared to 900 megahertz. If you use it, the antenna that you want to place at your receiver would be 3.3 nanometer away from the transmitter. The receiver is 3.3 nanometer away from the transmitter in assessment 2. In example 1, it is 6 meter away. The transmitter and receiver distance is 6 meter away. Whereas in assessment 2, it is 3.3 nanometer. So now you see, is there any use in placing a transmitting antenna and a receiving antenna with a separation distance of 3.3 nanometer? You justify and tell me in chat box. So this is what I thought of making a knowledge about it. So the choice of lower frequencies. If you use a lower frequency, the receiving antenna will fall at a lower distance, which is of no use of communication at all. Okay. So those who had worked out this problem would have understood definitely why assessment 2 I had given you, or what could be the distance between the transmitter and receiver, or why communication is being effectively used. Okay. Thank you for your valuable answers, for a valuable consideration in taking some time to solve this assessment 1 and assessment 2. Yeah, you can see in chat box the attendance sheet for today's session. Those are filling. This form will only be given attendance, so kindly check it. The link will be active only for 10 minutes, that is till 4 p.m. Kindly check in chat box.